Welcome to the Deep Dive, everybody.
Hi, everyone. And
Today we're diving into A Brief History of Time by Stephen Hawking,
yes.
which is a book that one of you requested. So
yes, it was.
we're very excited to take a look. It's a really influential science book published way back in 1988.
Yeah.
And it's become a modern classic.
Yeah.
So we are going to explore some fascinating questions, like how did the universe begin? What are black holes? Is time travel possible?
Big questions.
So chapter 1, we start way back with the ancient Greeks.
Yeah. We go way back.
What were some of their thoughts on the universe?
Well, they were very keen observers, even though they didn't have any of the fancy equipment that we have today.
Right.
But Aristotle, for example, he figured out that the Earth was a sphere just by watching ships kind of go hull first over the horizon, and also by watching the Earth's curved shadow during lunar eclipses.
That's really smart for 2,000 years ago.
Yeah, so he was onto a few things.
Yeah.
But he also, of course, believed in the geocentric model of the universe with the Earth at the center.
Yeah.
And that idea was backed by the church for centuries.
Yeah.
So it was the prevailing idea.
Everyone's comfy with this Earth-centered universe. Chapter 2 comes along, and we've got Galileo in the 1600s.
Yeah.
He shook things up a bit, right?
He did, yeah. So Galileo was the first to use a telescope for astronomical purposes.
Oh, okay.
And he observed 4 moons orbiting Jupiter.
Wow.
Which was quite a discovery at the time.
Right.
Because, it was the first time anybody had seen celestial bodies clearly orbiting something other than the Earth.
Yeah.
So that was a blow to
the
geocentric model, and it provided evidence for the heliocentric model with the sun at the center.
Okay, so the universe is no longer this comfy little snow globe with Earth at the center. Things are getting bigger. What happens next?
Well, then we get Sir Isaac Newton in the same chapter, who, came up with his laws of motion and universal gravitation, which were revolutionary at the time because suddenly we could predict the movements of the planets and stars with incredible accuracy.
But even Newton's laws had their limits, right?
They did, yeah. As our understanding of the universe expanded, as we learned more, some cracks began to show.
Okay.
So, for example, when applied to the vastness of space, Newton's laws couldn't quite explain certain phenomena, particularly those involving very massive objects or speeds approaching the speed of light.
That takes us to Chapter 3 in Einstein's theory of relativity.
Yes.
Now things get really interesting.
It does, yeah. Einstein completely revolutionized our understanding of gravity by showing that it wasn't simply a force, but a curvature of space-time itself caused by mass and energy.
Okay.
It's kind of like, imagine a bowling ball on a trampoline. It creates a dip, right?
Right.
So that's kind of how massive objects warp space-time.
Okay.
And this curvature also affects the flow of time.
Yeah.
Time actually slows down near massive objects.
Whoa.
Yeah.
So
I am blown.
It's pretty amazing.
So that brings us to Chapter 3 and Edwin Hubble.
Yes.
Who in the 1920s discovered that the universe is expanding.
Yes.
How did he figure that out?
So Hubble was observing distant galaxies.
Okay.
And he noticed that they were moving away from us. And the farther away they were, the faster they were receding.
Okay.
And that led to the Big Bang Theory.
Right.
The idea that the universe originated from an incredibly dense, hot state.
Okay.
And has been expanding and cooling ever since.
So we're talking about a universe that's constantly growing, evolving. What about the tiny stuff?
Yeah.
Building blocks of it all. That's where Chapter 4 comes in.
Yes. And this is where we get into the realm of quantum mechanics.
Okay.
Which is a mind-boggling world.
Where things behave very differently from the everyday world that we experience.
Right.
One of the key figures in this chapter is Werner Heisenberg and his uncertainty principle.
Okay, the uncertainty principle. So some things in the universe are fundamentally unknowable.
In a way, yes. So Heisenberg's uncertainty principle states that you can never know both the exact position and the exact momentum of a particle at the same time. The more precisely you measure one, the less you can know about the other.
So that's Almost sounds like something out of a philosophy book.
Yeah.
What does that mean for our understanding of reality?
I think it challenges the idea that the universe is completely deterministic.
Okay.
So at the subatomic level, there's an element of randomness and probability,
Right.
meaning even if we knew every single law of physics, we still couldn't predict the future with absolute certainty.
That's both unsettling and exciting.
It is, yeah.
So we've got this expanding universe governed by these weird quantum rules.
Yeah.
What about the forces at play?
Well, that's what Chapter 5 is about. So in this chapter, Hawking talks about the four fundamental forces that govern everything in the universe. Gravity, electromagnetism, the weak nuclear force, and the strong nuclear force.
So gravity keeps us grounded. Electromagnetism powers our electronics.
Right.
What about the other two?
So the weak nuclear force is responsible for radioactive decay.
Okay.
And the strong nuclear force holds the nucleus of an atom together.
Okay.
And what's fascinating is that physicists have been trying to develop a grand unified theory that could explain all these forces within a single framework.
It's like finding the ultimate recipe that explains how the universe cooks up everything we see.
You could say that, yeah.
I'm guessing black holes play a big role in this quest.
They do.
Because chapters 6 and 7 seem to be all about these enigmatic cosmic objects.
Yes.
What exactly are black holes?
Well, they're regions of space-time where gravity is so strong that nothing, not even light, can escape.
Okay.
And they form when massive stars collapse at the end of their lives, crushing themselves into an incredibly dense point.
So nothing can escape. How do we even know they exist?
So we detect them indirectly by observing their effects on nearby matter.
Okay.
So if a black hole is pulling in gas and stars, it creates this swirling disk of superheated material that emits X-rays, which we can observe from Earth.
So even though we can't see them directly, we can see their gravitational shadow play.
Exactly. And Hawking also made a groundbreaking discovery in the 1970s that black holes aren't entirely black.
Wait, they emit light.
Well, not exactly light. They emit a faint radiation due to quantum effects near their event horizon, the point of no return. And this is known as Hawking radiation. And it implies that black holes actually slowly evaporate over time.
Black holes aren't eternal.
No.
That's wild.
Yeah.
I'm guessing that this discovery sent shockwaves through the physics community.
It did, yeah. It had major implications for our understanding of black holes.
Right.
And even for the search for a unified theory of physics.
I'm ready to dive deeper into that, but it looks like we're out of time for this part.
Okay.
Don't worry, though. In the next part of our deep dive, we'll explore how Hawking connects black holes to the Big Bang, delve into the mysteries of time, and tackle the quest for a theory of everything.
It's going to be a wild ride. Welcome back to our deep dive into a brief history of time.
Yeah, my brain is still trying to process that whole black holes evaporating thing.
It is pretty wild. Yeah. But let's move on to Chapter 8, where Hawking takes us back to the beginning of everything, the Big Bang. He suggests that by studying black holes, we might be able to get some clues about the very, very early universe.
How does that work? How are they connected?
Well, just moments after the Big Bang, the universe was incredibly hot and dense, which is actually pretty similar to the conditions inside a black hole.
That's a good point, yeah.
So, by understanding how black holes work, we might be able to learn more about the universe's birth.
Okay, that makes sense. Now, didn't Hawking have some pretty interesting ideas about how the universe expanded in those first few, fractions of a second after the Big Bang?
He did. He was a big supporter of the theory of cosmic inflation, which says that the universe expanded super, super rapidly just moments after the Big Bang.
Okay.
And this actually helps to explain why the universe looks so uniform on a large scale, because it all started from this tiny little region and then just blew up like a balloon.
The balloon analogy, I like that. Okay, so we've got this universe born from a hot, dense state, expanding rapidly, and it's still growing today, billions of years later. But what about the direction of time? Why does time always seem to go forward? That's what he talks about in Chapter 9, right?
Right. This is where he gets into the arrow of time. Hawking links the arrow of time to the second law of thermodynamics.
Okay.
Which states that the entropy or disorder of a closed system always tends to increase over time. So basically, things get messier.
So time moves forward because everything gets messier. That's a little bit depressing.
Well, think about it this way. It's really easy to break a glass, right? It's pretty hard for those broken pieces to put themselves back together. There's this inherent asymmetry in the universe that gives time its direction.
Yeah, okay, I get it. So did that mean no going back in time to undo those embarrassing moments?
Well, probably not. I mean, the equations of general relativity actually do allow for the possibility of time travel, but the practicalities and paradoxes, make it very unlikely. So for now, at least, it's probably best to leave time travel in the realm of science fiction.
I mean, I've seen enough movies to know that time travel can cause some serious problems.
Exactly. And speaking of science fiction, Hawking actually explores wormholes and time travel in Chapter 10.
Okay, now we're talking. Wormholes. Those always sounded pretty cool in those sci-fi movies. Are they actually possible?
Well, wormholes are these theoretical tunnels through space-time, and they could, connect really distant regions of the universe.
Okay.
And, while they're allowed by the equations of general relativity, we still haven't seen any evidence that they actually exist.
So they're still theoretical.
For now, yeah.
What about time travel? I mean, could we ever build a time machine?
Well, Einstein's theories don't exactly rule out time travel.
Right.
But it just creates so many paradoxes and inconsistencies.
Yeah.
Like, what if you went back in time and accidentally prevented your own birth? Things get really complicated really quickly.
Yeah, I can see how that would be a problem. So maybe we should leave the time travel to the movies.
Probably for the best. Okay, so we've talked about the Big Bang, we've talked about black holes, the mysteries of time, and even a little science fiction. But one big question that keeps coming up throughout the book is the search for a unified theory.
Yeah, he definitely keeps coming back to that.
And he really dives into it in Chapter 11.
Okay.
This is like the holy grail for modern physics. Trying to find one theory that can explain all of the forces and particles in the universe. It would bring together Einstein's theory of general relativity, which explains gravity, and quantum mechanics, which explains the other forces.
So it's like finding the missing piece of the puzzle that connects the universe's biggest and smallest components.
Exactly. And it's a challenge that's occupied some of the best minds in physics for decades.
Now, is there any theory that, comes close to actually unifying everything?
Well, string theory is a big contender.
Okay.
It suggests that the tiniest building blocks of the universe aren't these little point-like particles, but these vibrating strings.
Okay.
And it's the different vibrations of these strings that give rise to all the different forces and particles that we see.
So are we any closer to finding this unified theory?
It's still a work in progress. String theory is a very, very complex idea, and it hasn't been experimentally verified yet. But it offers a really fascinating glimpse into a deeper level of reality.
Sounds like we still have a lot to learn about the universe.
We do, and that's what makes it so exciting.
I totally agree. Now, we did touch on how, a brief history of time has been called a bit dense.
Mm-hmm.
What advice would you give to someone who might be intimidated by the book, but still really wants to learn about these big ideas?
Well, first of all, I'd say don't be afraid to take it slow. Don't feel like you have to understand absolutely everything on the first read.
Okay.
It's okay to reread certain passages or look up terms that you don't know or even skip ahead to chapters that sound interesting.
Right.
And there are also, a lot of resources out there, online summaries, documentaries, podcasts like ours even.
Right.
Don't be afraid to talk about the book with your friends, maybe join a book club.
Yeah.
The important thing is to enjoy the process of learning.
It's a journey.
Exactly. And that's really what A Brief History of Time is all about, sparking that curiosity and sense of wonder.
Yeah, it definitely is a journey. And even though we tried to make it as accessible as possible, I'm sure some people are still going to find it,
A little dense, yeah.
Yeah, a little dense.
It's a lot to take in.
So what advice would you give to someone who's maybe intimidated by the book, but still, is curious and wants to explore these topics?
I think the best advice is don't be afraid to take your time with it.
Yes.
You don't have to understand everything on the first read.
Right.
Go back and reread passages if you need to.
Yeah.
Look things up if you don't understand them.
Yeah.
You can even just skip ahead to the parts that sound interesting.
Right.
There are a lot of different ways to approach it.
Right.
And the important thing is just to enjoy the process.
Mm-hmm.
I think, there are lots of resources out there to help you along the way if you get stuck,
There are summaries online. There are documentaries, podcasts. Exactly.
Right.
And you can always, discuss the book with friends or
Sure.
join a book club.
Yeah. I like that.
Just to kind of share your thoughts and questions.
Yeah, it's a reminder that learning about the universe should be fun.
Absolutely.
It shouldn't be a chore.
Yeah.
So as we wrap up our deep dive here,
Yeah.
what would you say is the most important takeaway from a brief history of time?
I think for me, the biggest takeaway is just the realization that, we're part of something so much bigger than ourselves.
Yeah.
This universe is vast and mysterious and
Yeah.
still largely unknown.
Yeah.
But as Hawking shows us, it's governed by these laws that we can strive to understand.
Right.
And by asking these questions, we push the boundaries of human knowledge and come a little bit closer to understanding our place in the cosmos. I like that. So it's really the journey of discovery and knowledge it's the most important thing.
Yeah, I think so.
Well, thank you so much for taking us on this incredible journey.
Of course.
Through a brief history of time.
My pleasure.
And to our listeners, thank you so much for joining us.
Yes. Thank you.
We hope you've enjoyed this deep dive.
Yeah, thanks for listening.
And till next time, keep looking up at the stars.
And keep wondering.
Keep wondering.